Okay, so no lab this week. But if you have any questions about problems or anything, I'd be happy to, answer questions after class. So keep that in mind if you want to bring stuff. And last time, we started talking about Newton's second law. And I said it's the most important equation in the whole class. So this is an exciting time to be alive. And then we used Newton's second law, N2L, to calculate the force, the weight force, the force applied by gravity. And what we got for the weight force was the mass times 9.81 meters per second squared acting down. M is the object's mass. G is positive 9.81 meters per second squared. And then if you use the positive direction up, like we always do, well, there'll be a couple cases where we won't, where it'll be better to use something else, but most of the time we do. Then 9.81 meters per second squared down is 0, negative 9.81. So one thing that I said to be sort of conscious of, an easy, a pitfall that's easy to make, is that when something's in free fall, well, two objects that have different masses have different forces applied to them by gravity. So if two things with different masses are both in free fall, there's a bigger force on the more massive one than the less massive one. Like a bowling ball has a bigger force on it than a tennis ball does. But because of Newton's second law, even though they have different forces on them, the acceleration ends up being exactly the same. And so just like we've been saying since basically the beginning of the class, if you don't have any air resistance, a tennis ball or a pebble and a bowling ball will fall exactly the same, even though one has a bigger force on it than the other one. It's easy to get confused about those two things. Okay, so now what we're going to do, any questions about that stuff from last time? And so now what we're going to do is start to calculate the other types of forces that act on bodies using Newton's second law. Given that, now we know the force applied by gravity, we can use that to calculate some other forces. So now use that weight to calculate contact forces. Okay, so here's an example. Let's say that there's a scale resting on the ground and a person on the scale. And let's say the person has a mass of 50 kilograms. like 120 pounds or something. And we want to know what's the force the scale applies to the man. Pretty soon we're going to start talking about what we know about the directions of force vectors that are applied by contact forces, but for now we'll assume we don't know anything about the direction. We can still calculate it in this case. So Newton's second law says add up all the forces. So it says choose an object, and we're going to choose the man. And then add up all the forces acting on that object. That has to be equal to the mass of the object times the acceleration vector of the object. So Newton's second law says add up all the forces. That's F net. That's equal to the mass of the chosen object times the acceleration vector. So what forces are acting on the man? There's two of them. There's gravity, and if we choose the y-axis up, we know that gravity is acting down, so that's in the negative y direction. So that says 0, negative 50 times 9.81. That's the weight. Question? And then the only other force acting on the man is the contact. There's contact between the scale and the man's feet. So I'll call that force from the scale, and I'll break it up into x and y components. And now that we've added up all the forces on the man, that has to be equal to the mass of the man times the acceleration. This guy's just standing here. What's his acceleration? 0. There's no velocity, so the velocity isn't changing, so acceleration is 0. And now I'll break this up into x and y components. So I'll break it into one equation for each component. So the x equation says 0 plus force from the scale x component is equal to 50 times 0, which is 0. And the y equation says if you multiply negative 50 times 9.81, you get negative 490.5 plus the force from the scale y is equal to 0. And so F scale x is equal to 0 from the first equation, and F scale y is equal to positive 490.5. You just have to do the algebra. Because he's... What?
No, F scale x. But you said plus F scale y. Wouldn't it be plus 0 equals negative
The stuff in the x component of these vectors, that's its own equation. And the stuff in the y components makes its own equation. So we have one equation that says 0 plus f scale x is equal to 50 times 0. And then we have one that says negative 490.5 plus f scale y is equal to 50 times 0. Yep. And so the force vector, if you now combine these back into like a vector form, you get that f sub scale is equal to 0, positive 490.5 newtons. And so let's think about what that means. So if this is the coordinate system, this is the x-axis, y-axis, and in this coordinate system, if we plot this as a point, we go 0x, positive 490.5 y, and then we draw the head there and the tail at the origin. This black vector has a magnitude of 490.5 newtons, and that's the force the scale applies to the man. And if the scale didn't apply that force to the man would sink into the scale, into the floor. You know what I mean? That upward force is what counteracts the force of gravity and lets the man stay in place instead of accelerating downwards. And that's how a scale works. A scale is actually, the scale isn't directly measuring how much force gravity applies to you. It's just measuring how much force it's applying to your feet, And so it measures this force of 490.5. It tells you that's the force that it's applying to your feet. And then as long as the only two forces acting on you are that contact force and the weight force, then that has the same magnitude as the weight force. If you like Homer Simpson, where he's trying to gain 300 pounds so he can work from home, and he's like weighing himself and he's disappointed because he hasn't gotten heavy enough yet. But then it turns out his gut is hanging on the towel rack, and so he's actually like way heavier. So if your gut's hanging on the towel rack, then the scale is not accurately measuring how much force gravity is applying to you, because then there's a third force in there that you don't know, and this equation gets all messed up. Okay, so let's do a similar one. Yes?
Can you just explain one more time on how you know it's 490.5 to the f scale of y?
Yeah. So first I wrote this out in a vector form, Newton's second law. And the way vectors always work, if you have a vector equation like this, you can take all of the x components and treat that as a single equation. And you can take all the y components and treat that as a separate single equation. So I took all of the x components and wrote this single equation that says 0 plus f scale x is equal to 50 times 0. That was the first equation. And then I wrote the second equation, said negative 490.5 plus f scale y is equal to 0. So those are the two equations.
So you would have to add 490.5 to 0.
Yep, and then you just use regular algebra to solve. Yep. Yes.
So we're basically solving for f scale x and f scale y?
Yes.
Okay.
Exactly. Yep.
In the weight, that the part I'm a little confused.
Mm-hmm.
Where did the minus 50 times 9.1?
Where'd it come from? Okay, so here's what we know about, we've chosen this coordinate system with x-axis horizontal and y-axis up, okay? And here's what we know about the weight. We know that it has a magnitude of mg, so we know it has a magnitude of 50 times 9.81, or 490.5. And we know it acts down, because that's what weight does. It just acts down towards the center of the Earth. And so now we just have to come up with the components in this coordinate system that we've chosen. And there's two ways you can think about it. One is you can think, what's the counterclockwise angle to get from the positive x-axis to here? 270, or you could go negative 90. So it's 490.5 times cosine and sine of 270, or 490.5 times cosine and sine of negative 90. It gives you the same thing. And what do you get if you do that? You better get what I put. You know, so it gives 0, negative 490.5. The other way to think about it is just remember that the components of this vector are the coordinates of the head when you put the tail at the origin. So if it's 490.5 in the negative y direction, then those coordinates are just 0, negative 490.5. So either of those two ways of thinking about it give you the same answer. And the answer is 0, negative 490.5. What is? Well, for the answer, it's positive once you solve for f scale y. But when you put it in as the weight, it's negative. And then you just use algebra to solve for the variable. F scale y is just a long name for a variable. It could be x or y or whatever, you know. Okay. Any other questions about that? Well, let's do a similar one now. So same guy. But now the scale is on an elevator that's accelerating upward at, I don't know, 1 meter per second squared. So the scale's still there. Same guy. And this time the elevator's accelerating up at 1 meter per second squared. And we want to know what's the force the scale applies to the man. Well, we're going to use Newton's second law again. And the same two forces are acting. The only forces acting are the weight, and then the one contact force, which is the force pushing on his feet, you know, provided by the scale. So it looks the same at the beginning. We have a weight of 0, negative 490.5, plus F scale x, F scale y. And that's equal to the mass times the acceleration. The mass is 50 kilograms. So now this is where things are going to change. In the last example, there was no acceleration. Now we have an acceleration upward of 1 meter per second squared. What's that in components? Yeah, 0, positive 1. So if you have, if this is 1 meter per second squared, and we're trying to represent the components in that coordinate system, you can think of that as an angle of positive 90 degrees, or you can just think of it as in the positive y direction, so it's 0 for the x component, positive 1 for the y component. So now the acceleration is 0, 1. And I'll break it up into an x equation and a y equation. The x equation says 0 plus f scale x is equal to 50 times 0, so that's just 0. And the y equation says negative 490.5 plus f scale y is equal to, this time you have 50 times 1, so 50. If you solve the x equation, you get that f scale x is equal to 0. If you solve the y equation, you get f scale y is equal to 50 plus 490.5, so 540.5. And if you put that back in a vector form, you get 0, 540.5, or 540.5 newtons up. Yes?
Okay, so there's just like a lot of numbers and you just need to organize.
Yeah.
So the vector component that's by 50, that's, so 50 is the mass.
Yep.
And then 0, 1, that's the acceleration
Right.
vector, correct?
Yes.
And then so what would you name the vector underneath in 2L? The 0 and the negative 49.
This?
No, above. Yes. What's that vector?
This?
No, to your left.
This?
Yes.
That's the weight.
That's just the weight.
Yep. So that's the force applied by gravity, and that's the force applied by the scale. And those are the only two forces.
Thank you.
Yep. So when an elevator is moving, it can do two things. It can be accelerating, or it can be moving with a constant velocity. Most of the time it's moving with a pretty constant velocity. But at the start, when it starts going, it accelerates, and this effect holds for that short time until it gets up to like its final speed. And so what this says is, when an elevator, if you're standing on a scale in an elevator, and it starts to go up, for that little period where it's accelerating, the scale that you're standing on would read a higher value. And that sort of makes sense with the experience of being on an elevator. You feel, like you can sort of feel it in your legs when it starts to go up. Yep.
So if it was accelerating down, it would be negative, so that's 0, negative?
Yeah, so that's what I want you to do now. Let's just do the same thing again. So now the elevator is accelerating downwards. At 1 meter per second squared. And what's the force applied to the man by the scale? Okay, so see if you can work through that, compare answers to each other.